Okay, so we have two matrix model talks in this first block, and it's a pleasure to have Adrien tell us about lower D matrix models.
Okay, thank you, Pedro. So, good morning, everyone. First, I would like to thank the organizers for letting me the opportunity to talk about these models. So, this talk will be in the context of the polarized IKKT model. So, I hope you went to João's talk yesterday. And we believe matrix models are very interesting models where we can find gravity, like some of the easiest models we can think of. So the idea of this talk is that we will look at what are the essential properties of polarized IKKT, and we will see that, we will basically find a landscape of models that have the same structure as polarized IKKT in different dimensions. So I will start the talk by explaining each of these words. So what is matrix model, what is super Yang-Mills matrix model, and what is a massive deformation. So first, what is to be precise, Hermitian matrix model. So it's a model where we have, let's say, D bosonic matrices, so simply D matrices with whose components are numbers, and curly N Hermitian matrices. So each component of these curly N matrices are Grassmann numbers, so they're anti-commuting numbers. And then the model is, if you want to compute expectation values, it's like random matrix theory, except that we allow for fermions, which is a bit a special feature. But if you look just at, so that's the way we define the model, and then the partition function is just given by this interval. So that was for what is a matrix model. Okay, so it's very concrete. It's just a set of integrals, right? There is no.
Is there a pointer here?
Okay. But okay, I can continue while.
Yeah.
So right, it's a simple set of integrals, right? It's a finite number of integrals if n is finite, which is very special compared to usual cases of quantum field theory. So now what is a Yang-Mills matrix model? So, yes. Thank you. Sorry, yes. Okay, good, thank you. Right, so as I said, this set of integrals is a finite number of integrals, which is to contrast with the usual case of quantum mechanics or quantum field theory, where we have a path integral. Here it's really a finite number. Okay, now I want to explain what is a Yang-Mills matrix model. So you may say that Yang-Mills doesn't mean anything in 0 plus 0 dimensions because it's just invariance under UN, right? Or SUN. But here I have in mind that we start from a d-dimensional Yang-Mills theory, pure Yang-Mills theory, say in Euclidean space-time, and we dimensionally reduce down to a point. So you see that dimensional reduction in this case is very easy. I just drop derivatives. So if I drop this derivative and this derivative, I just get the commutator squared in f squared, and that's it. So this is what I call a Yang-Mills matrix model, and here, let's say, in d dimension. Now, what is a super Yang-Mills matrix model? Well, it's the supersymmetric extension of Yang-Mills. So this only exists in specific dimensions, 2, 3, 4, 6, and 10. And it has the following form with kind of a Yukawa term. And now I claim that this model is supersymmetric. So there is some transformation delta, which sends bosons to fermions and fermions to bosons, parameterized by a parameter epsilon, which has n degrees of freedom, such that this is invariant. This is 0. So that's what I will mean by a super Yang-Mills matrix model. Now, what is a mass deformation? What is a massive super Yang-Mills matrix model? Well, I start from super Yang-Mills, and I allow deformations in the following sense. So I will work in units where G Yang-Mills has dimension 2, and X has dimension 1. So what I mean is that I consider a mass parameter mu, which has dimension 1, and I allow for the following deformations. So in these units, V1 has dimension 3. So the only way to build operators of dimension 3, and I forgot to mention, sorry, psi also has dimension 3 halves. So the way to build dimension 3 operators is either by considering 2 fermions or 3 bosons. Okay, so that's what I mean by V1. And then for the other term, V2, it has dimension 2. So the only way to have dimension 2 in my units is just x squared.
So
Basically,
dimension here,
yeah, this is, so indeed, it's a bit, you may say, why am I doing this? Why am I scaling j numbers out of the integral, etc.? So the direct question is, the direct answer is basically I'm doing like in polarized AKT. This is exactly the form that polarized AKT has. Now I allow V1 and V2 to be generic. But the more pragmatic answer is that I want to deform this action by something that when x is very large is subleading compared to the original piece. Okay, so if you want, that's a convincing argument. But okay, in practice, that's my rules, that's my set of rules, and that's what I'm gonna assume for this talk. Okay. So now, yesterday, I hope you saw what is I believe, the most interesting massive superlinear matrix model, which is the polarized AKT model. So the polarized AKT model, I remind you the action, it has exactly the form I mentioned before. There is this term with 3 matrices that has this epsilon, and then there are mass terms for the bosons and the fermions. So it's a model in 10 dimensions which has 16 supersymmetries, and we'll see that in fact it's the unique model, but this we'll see afterwards. And so this is the interesting model which has some very nice holography that it should be dual to Euclidean geometry.
So in each dimension, you mentioned that in certain dimensions we have a super Yang-Mills model, and each one of them has such a massive deformation, right?
Yes.
Okay.
Yes.
Can everyone hear properly? We don't need microphone for the audience, right? Okay.
So yeah. What is the motivation also for constructing these models? You may say, okay, we have polarized AKT, why do I care about classifying all such models? Well, there is one issue in polarized AKT, which is this sign problem, that if you consider expectation values of bosonic observable, and you integrate out the fermions, you get a Pfaffian. Basically, Pfaffian is like square root of determinant in some sense, but you have to be careful because there's an overall sign, but basically it's like the square root of the determinant. So that's what you get from integrating out fermions, but this thing is more special than square root of determinant. It can change sign. And that's what happens in polarized AKT. This thing changes sign. The square of this is equal to a determinant, but it can change sign because it can go cross 0. So it's not positive for all x, and we'll see that we will construct models where it's actually positive for all x in some specific dimensions. So that's if you want, the application of this story. So in today's talk, I will classify all massive superlinear matrix models in 2, 3, 4, 6, and 10 dimensions. So the outline is the following. I will start by explaining the idea that allows this classification. Then I will give you the list of all the models I constructed. I will mention what we can compute in these models. And finally, I will discuss an interesting case where the Pfaffian is positive. So let's see how we can classify. So I remind you that in my construction, the action takes the following form. It's a generic mass deformation in this sense. So we have 3 unknowns. We have M, which is a matrix with spinor components. We have S, which is a 3 tensor, which has to be cyclic. And we have T, which is symmetric. Okay, so for now, these are the 3 parameters that I want to fix. Now, we require that this is invariant under curly n supersymmetries. So the generic form of the supersymmetry is the following. So this first term is the pure Yang-Mills matrix model supersymmetry transformation. And then I allow deformations of this transformation. And so if I do some dimensional analysis, I will see that in my units, these theta's all have to vanish because I have no way of constructing something that has dimension half here. That's basically the dimensional analysis. Now, this A1 is the only parameter that can be non-zero because it has to have dimension 1 and it has to be bosonic. So that can be linear in the boson we have, xi. But there is an arbitrary fermionic matrix because this A1 right? Psi is a spinner, epsilon is a spinner. So when I can act arbitrarily on epsilon with a matrix, a spinner matrix, a matrix with spinner components. So that's my fourth unknown, F, okay? And now, basically what I do is I impose supersymmetry, and I will get algebraic equations for O, M, S, T, and F, okay? So that's what we do. We require supersymmetry. So supersymmetry takes the following form. I can package together everything that appears at order mu, everything that appears at order mu squared. And both of these have to vanish, because this has to be true for all mu's. So the first vanishing gives me some equation in the space of, basically, this is a gamma matrix, right? F is a matrix also with spinor components, so it has curly n times curly n components. So I get curly n times curly n equations times the number of I and j's. So I get a lot of equations in this first equation, also in this second one. And basically, the idea is that in all dimensions, I can parameterize these f's and solve these algebraic equations. Okay. So that's the way we can classify all the superioris matrix models, massive superioris matrix models, in different dimensions. And the result is the following. So in d equals 10, we find that the only possible massive deformation is the polarized KKT model. So the polarized KKT model has SO3 cross SO7 symmetry. SO10 is broken down to SO3 cross SO7. And there is a single deformation parameter. And as I said, the Pfaffian is not positive. So there is the sign problem in this model. Now, when you do the story in 6 dimensions, you find that there are 2 types of models. The type 1 model, I call, breaks SO6 down to SO3 cross SO3. There is a single mass parameter, and the Pfaffian is not positive. Okay, I've also checked what is the supersymmetry algebra. The symmetry algebra, which is super algebra. And it is this D21 alpha equals a half. So this is an exceptional family of superalgebras that have been classified, where alpha in general is a continuous parameter. But in my case, I find that the only possible value it can take is a half. And that's very special. You may say, why not another value? I don't know, but this is an algebraic constraint that gives me alpha equals half. Now, there is also the type 2 model in 6 dimensions. SO6 is broken down to SO5. There is a single mass parameter, and the Pfaffian is still not positive. Now, in 4 dimensions, that's where I think I constructed nice models, because the Pfaffian here is positive. So these are models where we can run numerical simulations. We can run the Bootstrap. We can run Monte Carlo. And these models are interesting because the first preserves SO4, and it has a single mass parameter, whereas the second breaks SO4 to SO3, and it has 2 parameters. So these models I will describe in more detail afterwards. And finally, there is a single model in D equals 3 with 2 mass parameters that preserves SO3.
Sorry, I have
yes.
a few confusion about the mu parameter here. You are just giving all the massive parameters with
yes, so,
mu.
right.
I'm kind of confused why you can separate the, let's say, the super equation in the last slide in terms of mu and mu.
You mean why?
Yeah, so you just give them
It's a long question.
Yeah, so why you can separate them and claim that they vanish separately?
Right, so because this has to be imposed for all mu's, right? And when you have a polynomial equation that has to be true for all mu's, then each coefficient has to vanish, right?
Okay, but I still feel this is kind of arbitrary. But okay, we can discuss afterwards. Yeah.
But yeah, so but regarding your other question, why have I 2 parameters since here I seem to only have 1? Well, it's because there is a freedom in M, S, T, and F, and I find that everything is determined up to a single constant, right? So we have 2 parameters, mu and a constant. And then I called mu and S times mu two different things. Let's say that the constant is S. So then that's how you get two parameters. Okay. So now that we have these solutions, let me describe what we can compute generically for all these models. Yes. Sorry.
I was wondering whether you can obtain the same results starting from, say, supersymmetric quantum field theory in 4 dimensions with some mass deformations and dimensionally reducing that.
No, you cannot. So, for example, here in this paper, they constructed they did the same as I did, but for quantum mechanics. So they started from superharmonic quantum mechanics and they allowed for arbitrary deformations. Now, it turns out that if you dimensionally reduce these models, you get models that are not supersymmetric. Because in fact, the supersymmetric transformation in BMN depends on time. And so if I drop the time dependence, I drop some terms that arise from derivatives. So I will get a model that is not supersymmetric.
And you cannot fix this, for instance, turning on some background like you do some R-symmetry background, for instance, preserving at least some supersymmetry.
Yes, so if you want to get these models from dimensional reduction, I guess you should give mass to gauge fields, which means it's not gauge invariant. I would get, right? Okay, maybe it will become clear when I write one action, but when I give mass terms to gauge fields, basically. Okay. Right? So I don't know how you would get this from dimensional reduction. Right. Yes, I will. It's here, but okay, I will come to this. So as I was starting to say, there are things that we can compute, say at fixed time. So we can compute basically both limits, the limit of very large mass and the limit of very small mass. So in the limit of very small mass, it turns out that the off-diagonals are heavily suppressed, and you can describe the model in terms of only the diagonals. So, for example, if I want to be concrete, let's say I want to compute an observable like this, a function of x and psi. Then if I want to compute this in the very small mass limit, the strict massless limit, basically I should compute this expectation value only looking at the diagonal part of the model. So I'm basically dropping the commutator squared term, I'm basically dropping Meyer's term. I will get just a Gaussian, so this is easy to compute, this kind of expectation values. Right. Yes, and another thing is that for all models that I construct, the massless limit never gives the original pure Superyoung-Mills matrix model, the equivalent of IKKT in all dimensions. This is never recovered because here the masses are such that if you compute such observables, they all diverge in the massless limit. Now in the large mass limit, what happens is that basically the mass terms become more important than the commutator squared. So the commutator squared is effectively absent, and everything becomes purely Gaussian, and we can compute observables in this model. So that's the two limits that we can access. Now, as I was saying, the interesting time models are in 4 dimensions because the pathing is positive, and we could run numerics. So let me describe quickly what are the features. So for the SO4 model, there is only one minimum, which is the trivial minimum. It's just 0. And there's a single mass parameter. The one that breaks SO4 down to SO3, it has fuzzy sphere minima, like the polarized IKKT model, and it has 2 mass parameters. So in fact, it's even richer than the polarized IKKT. There are even 1 more parameter. So this looks like a very nice time model for polarized IKKT. It has the same features, also fuzzy sphere saddles, and all that. So let me write the actions to be more specific. For example, SO4 model. So the type 1 model has the following form. So this looks very like, if I want to write a mass deformation, this is the first thing I would write, right? Mu squared x squared and mu squared psi squared. And it turns out that's one solution that has some 4 supersymmetries in 4 dimensions. So to be very concrete, what is the integral that one needs to compute? It's that integral, right? So if I integrate out the fermions, remember I had psi squared, I integrate this out, then I get just this bosonic action, and I get the Pfaffian. Now, let me be more specific. What is the Pfaffian? So first, let me expand the matrices into SUN generators in the fundamental representation. So there will be n squared minus 1 components for each I. And now I can write x not in the fundamental as I did here, but I can rewrite it in the adjoint representation, which means that the components are given by the structure constants. So this is n squared minus 1 by n squared minus 1 matrix. It's a huge matrix. And now that I define these bold x, the Pfaffian of M basically takes this form. It's the Pfaffian of a 4x4 matrix where each component is a block of dimension n squared minus 1 by n squared minus 1. Now, I don't know if I have enough time. Okay, yeah, let me quickly describe how to show that this Pfaffian is positive. So the way to see it is first to notice that the one very important property of the Pfaffian is that its square gives the determinant. So now I want to compute the determinant of this matrix. So I can use some tricks of rearranging the columns and the rows, and I can write the determinant in terms of the following quantity. So H is now a 2x2 instead of a 4x4 matrix, where each block is still very, very big. And this is manifestly positive first, and it's also non-zero as long as mu is non-zero, right? So if mu is non-zero, there is no chance that this determinant can cross zero. It doesn't cross zero, so Pfaffian cannot become negative, because the Pfaffian is a continuous function of all parameters, x's and mu's. So if I fix mu to be non-zero, Pfaffian cannot change sign. It should cross zero to change sign. So that's why the Pfaffian is always positive in this model. Any question here?
So you showed that the determinant doesn't change sign?
Yes.
From that to the Pfaffian?
How can I see that no, sorry, I said that the determinant never crosses zero. It's never vanishing. Suppose mu is non-zero. If mu is zero, I can also show that the Pfaffian of the original IKKT model is positive, and that we will see the proof afterwards. Sorry?
So you have one point where it's positive and then it crosses.
Yes. So for mu positive, say mu is 1, okay? Then this is always non-zero, because it's like, yeah, you can write this a product of positive eigenvalues plus mu, right? So this is never zero, so the only way that the Pfaffian could change sign, since its square is something, is that this square gives zero, right? Here, determinant is positive. It's not a complex number. So if it were a complex number, I could go to a negative value without crossing zero. But here it's positive, so it has to cross zero to go to negative. Okay. Yes?
Click for this for a second. Maybe more than
I forgot. No, I know. Is it possible to write this directly the Pfaffian as some determinant of another matrix in this case?
Yeah, so you see, so now that I know that the Pfaffian is positive, I can write it as the square root of this determinant. That's one
that I
thing
know, but
first.
it's the square root of a big matrix.
Yes.
So there is no trick to write it as...
I don't know any. So yeah, it's true that maybe, okay, this determinant, maybe I could write as a square of something. And then, because, right, this is positive, so maybe it's the square of something, right? You see that it's h dagger h, so it looks like the square of that h, right? But I didn't find any way of doing it.
Yeah, with the mass, it's...
Yeah, with mass, it's a bit hard. Okay, so now let me discuss the other model, the one that breaks SO4 to SO3. So this model has the following form. So there are two parameters, mu1 and mu2. So for this quadratic term to be positive, I will impose that mu1 and mu2 are both positive or both negative. And the interesting thing of this model is that it has non-trivial saddles. It has non-trivial local minima. Yeah, I should say no, local minima, not because I drop the local maxima. So looking at the local minima, they take the following form where Ji is the n-dimensional representation of SU2, like Juan was explaining yesterday. So I have a lot of different saddles. I have the number P of n, the number of partitions of n as the number of saddles. And the ancient value is the following. So it means that the one that is leading, if I want to take a large mass, is the irreducible saddle, right? If you want to maximize trace of J squared, you should go for the irreducible saddle. So the irreducible representation of SU2. So that's the structure. Now I can again write explicitly the matrix integral.
Mu2 could also be negative, right? If mu2 was negative, then it would be the trivial vector.
If mu2...
No, sorry. No. I think it's better, sorry. I
Right.
did not see that it was a cube.
Yeah. Everything is to the fourth power. Right. So now I can again write explicitly the matrix integral. So I integrate out the fermions and I get just the bosonic part. Okay, I'm not writing it explicitly, but basically you remove the fermions. And now I have a Pfaffian, which again depends only on the, I have to write again this bold x in the adjoint representation. And right, and the Pfaffian now can be written as a determinant. That's a special property. So it's not that Pfaffian squared gives the determinant and then I do my tricks. It's really that the Pfaffian itself equals a determinant. There's an identity that when you have a Pfaffian of some matrix which is just zero, okay, I'm not going to explain that. There is an identity such that Pfaffian I can reduce to a determinant. And the determinant is given by this. And now I can show again that this is positive. So it's not trivial to see that this is positive. But the way to see it is, first I'm going to define A as being this matrix, and I want to show that the determinant of A is positive. So the way to do it is to look at the eigenvalues. We will see by looking at the eigenvalues that the determinant is positive. So let me define a matrix B in the following form. So this matrix B is such that its squared is minus the identity. And it's such that BAB is minus A star. So this you can check because bold X is a real number. It's a real matrix because remember the definition, right? It defined in terms of the structure constants which are positive. So it's a set of real numbers. So I know what is A star, and that's the identity I'm going to use. Because now suppose I have a vector V, which is an eigenvector of A, with eigenvalue lambda, okay? Then let me consider the vector BV star. Using this identity, I can show that the vector BV star is an eigenvector of A with eigenvalue lambda star. So to see this, you can just take the conjugate of this equation. You would get A star, and then bring B to the other side, okay? Yeah. So every time I have an eigenvector V with eigenvalue lambda, I also have an eigenvector BV star with eigenvalue lambda star. But V is not equal to BV star because of the following form for B. So that means I always have pairs, lambda and lambda star, in the spectrum of the matrix. So the determinant of A is a product of pairs, lambda and lambda star. So it's always positive semi-definite. Okay. So now let me mention, so that's it for this work. Now let me mention possible future work. So, yes.
Yeah, the determinant is positive, and then the Pfaffian is also positive due to the same reason. Is this the argument?
No. The Pfaffian is really equal to the determinant. That's what I was trying to say. It's not Pfaffian squared equals determinant. It's the Pfaffian is equal.
Pfaffian already equals
Yes.
the determinant. Okay, sorry.
Yes. Yeah, I don't know. I can read the identity, but. Okay, so is there any question before I mention the future work? Okay, so, right, so first point is that we could do numerical simulations of these models that I described. Because the Pfaffian is positive, there's no sign problem, we can really sample over these models. So one could do could apply bootstrap techniques that were applied for matrix models already in some cases. Or we could do standard Monte Carlo techniques. Okay, so that's one thing that I think is most like the direct application of this work. Then the second point is that I did not compute every possible thing I could compute in these models. One could do localization to compute this type of correlators. So that doesn't depend on dimension. We can also do localization not only in 10D, but also in lower dimensions. The only specialty is that this type of observables is trivial when you have an SO2 among X1 and XD. So it's only when SOD is broken that this type of observable is interesting. And finally, let me mention that here I was motivated to construct these models because I was looking for models that could have a positive Pfaffian. But it's also interesting to ask whether these models have physical applications, like, or physical, maybe not physical, but can be explained from string theory or could have a holographic argument in themselves. Like, are there some dual geometries, some supergravity that is dual to these models? I don't know. Maybe that's a question for the audience. Yes. So that's it. If you have any questions, feel free to ask. Thank you. Yes?
Thank you. I have two questions. So does your classification prove that there's no model where no supersymmetric matrix model where the condition for a saddle point is that the matrices satisfy some other Lie algebra besides SU2?
Yes.
Okay.
Yes.
I see. My second question is more vague. So in condensed matter physics, there's often a tension between the model being interesting and the model not having a sign problem. That generally the most interesting models are the ones that do have a sign problem. Do you see some such tension in the list that you found?
So, right, I can go back to the table. The answer is no. I don't see any difference, and that's surprising to me, because you see, why should 4D be special compared to 3 and 6D? If everything was positive here, then we could say, okay, maybe this is the reason why this is not solvable. So, like, we cannot do numerics here, but here we can do numerics, and that's because it's too trivial, as you said. But here,
well, I'm not saying it's trivial. No. I mean, often models without a sign problem are still interesting. There's usually the ones with the sign problem are more interesting.
But yeah, so yeah, I don't know. I just don't know. But yeah, at least, even though we don't know if there is a supergravity dual or if there is any gravity in here, at least we can look at things in the matrix model. We can ask questions that we cannot answer to in porous KKT that we can answer here. So that's the idea.
So you said when you have SO2 symmetry, there's no nice bosonic observables. But can you write down fermionic ones, like bosons plus fermions that you can do localization with? Because you just need something supersymmetric, I suppose. Right?
Yeah, I don't know.
Sorry, can you
I've-
repeat the question?
For
Yes.
localization, can you do things with bosons and fermions so that you preserve the supersymmetry? Because sometimes when you have SOD symmetry, there is no purely bosonic thing that is supersymmetric.
In terms of observable.
Yes, yes.
Yeah, so I guess you mean fermionic observables, right?
Yes,
Just
yeah.
fermionic. So, right, from the structure of the algebra, we need to ask that this thing vanishes for some observable, right? Fermionic observable. So, yeah, it could be. We didn't investigate, I'm not sure. But yeah, I cannot say for sure no. I think not, but I'm not sure. So.
People can continue asking informally questions, but
Yes.
let's thank Adrien. So you have now 10 minutes in case you want to change rooms. So we start at 10:45 in 10 minutes. Yeah, we finish. So the lecture upstairs is we coordinate. They also start at